So as has been said, my name is Honza Král. I actually work for a company that's called Elasticsearch that's behind the open source product, and this is what I would like to talk to you about. So let's dive right in. Once I find my mouse. Better. So what Elasticsearch is, I usually just show this slide and say that it's a very buzzword compliant thing. It can do distributed, it can do HTTP and JSON and REST, and it's open source, it's highly scalable, it can do search, can do analytics, and it's all based on Lucene, our most beloved search library that powers anything from Elasticsearch to the Jeopardy winning computer from IBM Watson. So that's what Elasticsearch is. And how do you use it? So first you need to install Zookeeper, then you need to edit some XML file. Now, you download it, you unpack it, you run it, you're done. That's how easy it is to start with Elasticsearch. If you do this multiple times, especially the step 3, you will end up with multiple instances. They'll automatically form a cluster, and you will be able to see the distributed nature firsthand. So this is how easy it is to start with Elasticsearch. But what can you do with Elasticsearch? The first thing you need to do is put some data in. So the first aspect of Elasticsearch is you can treat it sort of as a document store. You put data in, you can get data out, you can delete data, you can update data just using a partial document that will be merged, or you can send a script that will be run on the server to update the document. So classic stuff, nothing too surprising. What else would you expect from a product that's called Elasticsearch? Well, probably something like search. So the simplest way possible, you do _search. You can even do that in your browser, it will still work. And you just supply the queue parameter, and you're looking for a conference. But that's not very flexible. So instead, what that actually translates to is this guy over here. So if you take a look at it, we still do the search, but instead of the queue parameter, we were just passing in the body, and in the body there is a JSON, there is a query string query with conference and title Python. So a little bit more complicated. This is just here to show you that you can use all the power of Lucene query syntax, which is quite powerful, and it allows you to do a lot of things. But it's not very good usually to rely on mashing some strings together to create a query for you. So what your typical queries would look like is this. Now this looks very scary for if it's the first time you've seen anything like that. But what it basically does is it's a filtered query. So it has a query and a filter. More about that later. And the query is a bool query that has must branch. And there is multi-match, so against multiple fields, I'm matching Python, and it must not match PHP in the title. So what this basically means that if in title or in body, if there is Python, it will match. And I'm also indicating that the title is more important to me. What that means is that the score of the document, the order that I get the documents in, will be influenced by this. So if there is Python in the title, it will be more towards the top. Note that Elasticsearch would do something like this on its own because title is typically a shorter field, and shorter fields have a higher priority automatically. But if we have some domain knowledge, if we know that title is super important, we can always just tell Elasticsearch. The second part that's here is a filter. Filter is different from a query. Where query actually contributes to the score, filter doesn't. Filter just limits the result set. But it's way more efficient. It's cached, it can be reused over multiple requests, and even if you have some composed filters, so you can again do the bool in the filter, the caches for the individual filters will be reused. So it's very optimized, very fast. So that's why you should always use filters if you can, and only use queries if you must. Okay, now enough talking. Well, I'll still talk, but enough just empty talking. Let's show some code, hopefully. So, can you read this? Yes, perfect. So this is basically where we ended with the slides. So it's a filtered query. It's even simpler. We don't have the bool part. So it's a filtered query. There is a multi-match. We're looking in title and body for Python, and we're filtering by creation date. If we run this, it took 2 milliseconds. It talked to all the shards, blah, 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 not interesting in this moment. And here are the hits. So the first one is a question. So the dataset that I'm using for this is a dataset from programmers.stackexchange.org. If you're familiar with that site, it's a site for engineers to discuss programming issues. So you see here immediately that this is a question. Somebody is just learning Python and wants to learn something. So it works. But like this result, at least for us, note that typically it would be JSON, but YAML is more readable for people. So I just asked Elasticsearch to give me everything in the YAML format. But this isn't readable, so let's modify the query the first time, and we'll add a field. So we only want 2 fields back. We only want the title and the creation date to be returned. That way we can actually see what we're getting back. Note that for every document we have its index, its type, and its ID. Those are the 3 items that uniquely identify a document. Then we also have the score, how well the document matched our given query. We will try and play with that later. So the first step that we do is we just limited the fields that we're getting back. But we are also searching on the body, and we don't want to return the whole body because it's potentially huge. It would be very nice if Elasticsearch could just give us a highlight. So we specify a highlight for title and for body of fragment size 50, and what this will actually do is for each document, it will give us just the fragment of the body, just the relevant part where the query matched. So here we can see the Python. Elasticsearch even went ahead and highlighted it for us. So we have HTML emphasis mark tags around it. If we needed something else than HTML, we could definitely say so. So this is the first. This is first very nice feature that you can see. This is usually very hard to do after you've retrieved the results, because sure, for Python it's easy, but there is always a problem of lowercase, uppercase, you need to find it. And then Elasticsearch will actually do something like stemming for you. So if you're searching for running, and there is only run in the document, Elasticsearch will still find it and highlight it correctly, which is very hard to do on your own. Also, Elasticsearch can be made aware of synonyms. So, for example, if we are searching for Python, we could define in our index that py is a synonym for Python. So, if the document just had py in it, and we would be searching for Python, it would still match, and the py would still be highlighted. So let's complicate our query further. Now let's see. Let's look for a question that somebody asked, and they're asking for PHP, and they're not asking for Python. So basically, we are just looking for somebody really looking for an answer concerning PHP. So this still works. You can definitely see that there is PHP and there is no Python. So why am I showing you this at a Python conference? It's just a setup for the next query. Now, what Elasticsearch can do, it can have some relationships between documents. One of the types of relationships is a parent-child. I've set up my index in such a way that when I have a question and answer, they have a relationship. The answer is a child of the question. So now I'm using a hasChild query here. And I have the same query from last time, that it needs to have PHP but must not have Python in it. And now I'm adding the condition that the question also has to have an answer associated with it that contains the word Python. So this is basically just a fancy way to find trolls. somebody's asking for a problem with PHP, and somebody answers them, just use Python. Which we can all agree with, but it's usually not a very helpful thing to do in internet communities. Note that the results only contain the questions, not the answers. If we wanted the answers with Python, we would have to do a second round trip. So it's very limited, but even though this, in front of your eyes, I've just performed a join operation in a NoSQL data store. That's pretty impressive, right? No? No? Okay, I'll try better. I'll try better. So that concludes a little bit the search part of the exploring your data. The second part is some sort of analytics. So we've stuck with this query for so long. Let's keep it and add just few more things at the end. Facets. What facet is a fancy word that basically means an aggregation. And right here, I'm defining two aggregations. A terms facet, which will basically just take all the different values for the field tags and give me the number of documents that have that value. And also a frequency, which is a data histogram based on the field creation date and interval of month. So this will give me, per month, it will give me how many documents matches this query. So if we run this, we have our typical results. And at the end, we have the result of the facets. So there's 66 documents that have the tag PHP, 26 with programming languages, 21 web development, and so on and so forth. And the same for the date histogram. We have date times here, which I am not able to decipher by hand, but this will basically, in this month, there was one question like that, in this month, 6, and so on. Now, this might be very difficult to imagine why this would be useful. How this actually transform into something interesting, into something like this. This is the same data set. This is the same tool. So this is Kibana. Kibana is a small JavaScript tool that sits on top of Elasticsearch and runs these sort of queries. So here, what you can see, this is the date histogram. This is the aggregation by tags. So you see, over 16% of all questions on Programmer Stack Exchange deal with Java. Like, you can quote this to anybody who will tell you that Java is a simple language. Like, most of the questions people have about Java. The second one is C#. So, and we can filter easily. Just click on it. We see that there's been a filter added. We can remove it and go back to it. We can filter by some other time period. We can even do. We might not want months, but let's put it on automatic. And here I've defined 3 queries. This queries basically has how many comments does the question have? 0 to 2, 2 to 4, 4 and more. I see the aggregations here. Even in the date histogram, I see everything split into three result groups. And here I have the individual questions. I can click on them. I can read them in a table, or I can get the raw JSON value of the document. So very useful, and this is just JavaScript. Everything you see was actually computed by Elasticsearch, and this is just a fancy display for it. This is just to give you an idea what these aggregations might be good for. So back to code. Now I'll skip the last example for search because that's not very interesting, and instead I'll show you something very new, something that we are preparing for the next release of Elasticsearch that should be hopefully early next year, and that's aggregations. Now I've called facets aggregations before, and that's where we'll start. So we start with a with a very simple query. Again, filtered query, multi-match, filter, the same thing that we dealt every time, and these two facets, the terms facet and the date histogram. Again, if we run it, we see that we have the proper aggregations and everything works fine. So the first thing that we are do is just replace this word with aggregations, with this word. Otherwise, nothing has changed. It still works as expected, but now we have way more power. In Elasticsearch 1.0, there is a power of aggregations, and now we can compose aggregations. So previously, we only had a handful of aggregations available, and now we can basically create our own. So what this does is, so we still have the terms aggregation. So we still want to we are still interested in see the distribution across tags, and then inside of that we have another aggregation, and that's an average aggregation on the field comment count. So this will give us for each tag what's the average comments for the documents that match that tag. So one way to look at it is this aggregation let us define the buckets. Like, give me the buckets per field value, per tag. And this aggregation actually allows us to define what to do with the documents in the bucket. Give me the average of comment count. Again, frequency is unchanged. We'll use that later. So if we run this, we see here the same result. So there are 16 documents with the tag design, but we also see that the average comment count for the questions that deal with design is 6.363636. I'm not going to read the whole number. So that's ultimately way more powerful than just the facets, than just giving you the buckets and you cannot do anything with it. And just to show you how crazy you can go, I have a file called crazy.sh that should be an indicator. And this is one of the aggregations. So again, we start with the tags. Inside, we still have the average comment count, and then we go into comments. So this is the second type of relationships that documents can have inside Elasticsearch. The first type was parent-child, which are two independent documents that just share a relationship. One is a parent of the other. A child can only have one parent can have many children, so 1 to n. And the second type is nested, which is basically a subdocument. In our case, we have a question on Stack Overflow, and the comments to that questions are part of the document, but Elasticsearch is aware that they are documents on their own. You generally just don't want to talk to them individually, so you just store them with the question. So that's what we are saying here. We are going to facet on the nested documents, on the comments. And the aggregations that we'll run there is we'll have one. This is top commenters, which is a terms facet. So we take the author of the comment and we run a terms facet. So we'll get the buckets for each author. We'll get their comments, and for those comments we'll run the max score. So data is worth 1,000 words. So we have a term programming languages that has 73 documents. It has 6 comments by average, so there is no surprise that there is 402 comments for this tag. And the top commenters are people. The first one is called SK Logic. He wrote 17 comments, and his max score that he received for any of his comments is 3. So, and we have all the top 10 commenters for this tag. So in one pass, in a single query, we are able to do a fairly complex aggregation using Elasticsearch. It's still very fast. When I scroll up, this one took 118 milliseconds, which is fairly slow for Elasticsearch because I'm running it locally. I'm running it with all the data from Stack Overflow. If you run it again, notice that I've babbled previously something about caching. So if you run it again, it's already half. And now when I run it, everything is loaded into memory, and it just gets faster and faster. So this is aggregations. This is a new feature that will be in Elasticsearch 1.0. Hopefully early next year. So, any questions so far? Aggregation, search, everything is clear? Or have I completely lost you? Okay. So we seem to be doing well. So this is just an example of the query. We made it 90% there. What we actually left out, because I want to get to more interesting stuff later, is a custom score step. So we can take some value from the document and use it to influence the score. Not to sort by it. We could do that too, but that's not very interesting. We want to influence the scores. So for example, if you have a document that matches really well, but the users don't think it's a very good question, it shouldn't be the very top one. If on the other hand you have a document that doesn't match too well, but the users agree that it's a very, very good question, and because we have user-contributed data, this is Stack Overflow, so people vote up and down for questions. We can take that into account and give our users the best possible experience. So this is just a crazy query. And moving on. Oftentimes, people use search for auto-completion. And that's totally possible, but not very good. It is not very good because search has a high overhead, and it was not built to do auto-completion. There is another thing that's built to do auto-completion, and that is a suggester. So again, if we switch into code, so we can do. So let's start with some data. So here I'm just creating an index. It's going to be an index for conferences. So I'm going to store conferences, and I'm going to have events in there. So I run it. Index has been created, nothing interesting. Then let's put in a document. Let's put in a document representing PyCon PL. So there is a title, there is a body, and then there is a suggest field. So I have all the different inputs, what I want to autocomplete on. Then I have what the actual canonical representation should be. Then I have any arbitrary payload that I want to return to the user, and some weight. Weight in this case is just, it's pure business value. It's up to me. Elasticsearch will not help me with the score or anything. This is basically how important this conference is in my data set. So I just index this, done, indexed. And now when I want to run a suggester, so here I'm running a suggester on a single letter, P. And boom. So here is a suggestion for letter P is PyCon PL in Shirk, something. And I have the payload, I have the score. Everything was returned to me, and it is sorted by the score. Now you could do the same thing with search, with a few differences. We pride ourselves that our search is very fast. We are slow as hell compared to our suggester. Our suggester, if it takes more than a millisecond, you're doing something wrong. It should be that fast. How it works is basically it builds a very efficient data structure in memory. It's called FST. It's basically a finite state machine, a little bit more fancy. So any single search, any single suggest that you throw at it, it's at most just one pass through this very efficient data structure. This very efficient data structure is so efficient that if you want to complete on all the words that are present in English Wikipedia, the entire data structure will have 80 megabytes. So passing through 80 megabytes in memory in a very optimized format, it's really fast. And that's how we do it. We cheat. We just build everything into memory, and then we just go there. And we have very smart people who are able to figure out how to make it accurate and how to make it distributed and scalable. So suggesters, use them for autocomplete. You can even do fuzzy suggesters that will take into account typos. So if I were to write not PyCon but PyOCN, it will still find it. Those are a little bit more expensive because basically the algorithm needs to generate all the different typos and take those into account. But it's still absolutely feasible, and many people love it. Also, this is a great way how to offload some load from your search cluster, because if you have good auto-completion on your site, a lot of the people won't even search because they will get the result right away through the autocomplete. That's why the payload comes in, where you can have the ID and you can then redirect them somewhere or something like that. So that's autocomplete. What else do we have? Another type of suggester, the did you mean suggester, the spell checker. So what this actually does is, so you can search for Johnny Walker, but Johnny Walker is spelled differently if you mean different things. So we built a context-aware suggester that can take this into account. So let's create an index. Let's index a few documents. So we have 3 characters: Johnny Walker, Johnny Cash, and Johnny Mnemonic. Those are three existing words names, and notice that the Johnny is spelled differently for Johnny Walker. So if we do a search, somebody is trying to match the phrase Johnny Walker. There are no hits because they spelled it wrong. But how do they know? If they try to spell check individual words, it will not work. So this is the same search, but we also ask for a suggestion on the text Johnny Walker. And lo and behold, we get back the suggestion that maybe, did you really mean Johnny spelled differently, Walker? So this is what Google does. Admittedly, Google is a little smarter than us, but we do a pretty good job. We detected that the second part is spelled correctly, but the first part isn't. You can even ask Elasticsearch again to highlight the part that's different, so you can see, did you instead mean Johnny? So another suggester. This one is used as part of the query. So if you have any input from the user, you can also feed it to the phrase suggester, and it will tell you if it thinks that the user made any typos, if they're spelling things wrong, or anything like that. Again, there are a host of knobs that you can turn to tweak the performance and the effectiveness. Like, do we care about the length of the phrase? Can we only do 1 word, 2 words, 3 words? Of course, the complexity rises. Do we only account for 1 mistake or 2 mistakes? It's all configurable, and it will depend on your use case what would be the best setting for you. So that was another feature, and the last feature, for which I actually need to. And the last feature is a percolator. What a percolator is a reversed search. What does reverse search mean? So I have a setup here that I'll just run. And reverse search means that I'm not indexing documents and running queries. I'm indexing queries and running documents. So, for example, imagine that you have a site for real estate. Somebody's trying to buy or sell their apartment. So this is stored search. There is a user who wants to create an alert whenever there is a new apartment for sale that matches my criteria. I want you to send me an email. And typically that's a rather difficult problem. With Elasticsearch, it's built in. So here we have a query. We are looking for something that contains either Ruby or Python, and there are no hits. I just created the index now, so that should be a giveaway. But one way to do it is we can keep running this query over and over and check if anything has changed, if anything is changing. That's both expensive and hard to do. So instead, what we do, we define a query, and this one I actually fixed from RuPy. So this actually takes into account PyCon. So we define this query and we store it. We store this query as a percolator. We even name it. So it's named PyCon PL, and if we run it, it's stored. And it's just there. And then when a document comes in, so there is a new conference, we can just run the percolate, which is just a special endpoint here in the REST URL, and it will tell me, yeah, the query that you registered earlier under the name PyCon PL, that's the one that matched. So I have stored query. I run a document, and it will tell me which queries matched. This is something that can easily scale to hundreds of thousands of queries that you store in Elasticsearch, and then you run the percolation on. Some customers run Elasticsearch just because of this feature. Know that I set the location Poland there, and that's because I can filter which queries that I've stored I want to run against. I don't always have to run against all of them. If I have a million of them, it's usually that every document I only want to match against few. So this is here as part of the query, I specified arbitrary metadata, and then when I'm running the percolation, I can run any query against that metadata. That will first limit the queries that I'll try, and then I'll try those and get back the number, the queries that match. Okay, so that was Percolator. So those were some of the interesting features that I wanted to highlight, that I wanted to demo for you, and there is only one question remain to be answered. Is it web scale? Yeah. We have customers that have hundreds of terabytes of data in a single cluster. We have customers that are doing percolation over millions of queries. Anything is possible if you give it enough hardware. And if we still have some time left, we can show a quick demo on how this actually works. So let me just... I'm just switching versions, so that's why it was unavailable for a moment. So this is our cluster. We have three indexes. We have one big one tiny one, and one also very small one, only 3 documents, but this one has been created with default settings. Default settings means that we divide each document into 5 shards, and we have 1 replica for each shard. Notice that the cluster health is yellow currently because we have some replicas that are not allocated anywhere. So the cluster didn't lose any data, but it is a little twitchy that it cannot do everything that we ask it to. So if we just run another Elasticsearch by running the exact same command that we used to start the first one, they'll form a cluster. And now we have a second one, and he will slowly allocate the missing replica. So now the cluster state is green, and for load balancing purposes, he'll also take these two shards at one point or another. These two are pretty big, so it might take a while. So the cluster is automatically balancing itself. So if I start yet another one, the same thing will happen. The cluster now there were no unallocated shards, but the cluster will identify the biggest shard and it will spread it to the third one. So this is the elastic part of the Elasticsearch. We just keep adding nodes, and the cluster does what it does best, and it will actually scale. Also, what we can do is we can run a command and set the number of replicas. So the number of shards we cannot change. Once the index is created, the number of replicas we can change any time. So now I've changed the number of replicas to 1. So that means the cluster state is yellow because it doesn't have allocated all the replicas that I want, and it will slowly start allocating the replicas. It was very fast for the small index. For the big index, it takes a little bit of time. Note that this is another plugin for Elasticsearch. It's just JavaScript that just reading the APIs of Elasticsearch to get all the information of what's going on. So this is how we do high availability. This is how we do scaling. We just divide everything into shards, and then that's it. So that's all I wanted to talk about. So thank you, and if you have any questions.
Hey, a question about the suggester. You said that using the Wikipedia corpora, it's pretty fast. So how does it handle updates? For example, if there's an update coming every few milliseconds.
So it does handle the updates. So I've shown you the shards. That's how Elasticsearch works. Each shard works in a little similar manner using Lucene. Lucene works in segments, and segments, once they're created, they're immutable. And we create the suggester data structures on top of the segments, and then we just merge them together.
Okay, so
what does this mean for this is, for each segment, every index or every update will create a segment, pretty much.
Okay, but
for that it will have the FSD.
You rebuild the whole state machine.
I'm sorry?
You rebuild the whole state machine on
No, I have multiple of those finite state machines that I, at regular intervals, merge into bigger ones.
Okay, thank you.
So, can you tell us something about handling geodata, like distances and so on?
Yeah, well, we do geo. You can define a point, a polygon, a line, or something like that. You can run full spectrum of geo filters and queries.
Okay, and another question: how well it performs if you want to really customize the scoring, like your own scoring function?
So for that, you would want to look into the new version. So for example, so this is how it looks. So this is a function score, and all I did was I supplied a script that's written in a language that's called mval, and it will take the original score and multiply it by the rating that's scored inside, +1, because some of the ratings are 0. So just to fix that, this is still very fast. Okay, not on a note that I'm currently running 4 nodes on my single machines because I did the demo earlier. If I were to shut them down, it's much faster. It's also much faster in the newer version. And that was the long answer. The short answer is it really depends. There are customers that have great experience with it, and it just really depends what you actually want. If it's something simple like this, then it's perfectly fine. If it's something more complex, then it really depends, and also depends on how big a result set, not the original data set, but how the result set is big. What you can always do is you can do a rescore phase. So you get the results back, and then if it's a potentially expensive operation, so you get the results back, and only on the limited subset of results, you then run the rescoring functions and reorder everything. So there are ways how to deal with this. Unfortunately, it's let's talk afterwards, because this is a longer answer that's probably not relevant for everybody.
Okay, thanks.
Could you please tell a few words about the support of other languages than English? There are like some analyzers or something like this.
Yes, absolutely. So we are built on top of Lucene. So any plugin that you find for Lucene will work with Elasticsearch. Built in several analyzers for several languages. I'm not sure about Polish right now. I know that Czech is there, Hungarian is there, and those are algorithmical stemmers, which are very fast and not too good. Alternatively, what you can do is a dictionary stemmer, which just depends on the quality of your dictionary. So we have a Hunspell analyzer, which you just give it a dictionary. So there is a Hunspell dictionary somewhere for Polish. I would suggest looking into either LibreOffice or Chrome. They both ship with pretty decent dictionaries, and based on that, we can use that to do stemming. So you can even have different language per document. What we allow you to do there is you can define the analysis dynamically, that it would it would use a field lookup. So it would basically look into a field, and based on the value of that field, for example, a language field, it would use different analyzer per document. So you get one index and one document in Polish, one in Czech, one in English, and it will work. It will use the correct analyzers every time. Sure. Any more questions?
So no more questions. Thank you very much.
Thank you.